Hello. Welcome to the Institute of Navigation, Precise Time and Time Interval 2021 meeting. This PTTI talk, Geostamp for Legal Time Traceability and 4D GIS Applications, has been prepared by Brooks Harris, Cambria Ezel, and Sean Vauban. Brooks is president and founder of EDL Max. It is a software development and services company to the television and post-production industries. The company specializes in edit data management, timecode, and associated imaging, audio, and video technologies. Cambria is an executive in finance, as well as a licensed attorney with diverse experience in regulatory policy and compliance, securities law, and international trade. She currently serves as a director and in-house counsel to the Long Van Group. She graduated from Texas Tech University and received her JD from City University of New York School of Law. Sean is a director and principal investigator at Sync and Scale. It is a startup co-engineering partner of Microsoft, an OEM partner of HPE, and a research and development partner of NIST, Time and Frequency Division. This talk describes an aggregate of two efforts: the Common Calendar Timestamp System by EDL Max, and Modern Timekeeping for IT Solutions by Sync and Scale. These were presented separately at past PTTI conferences in 2019 and 2020. We're now sharing a progress update of our collaboration since then. Our collective effort introduces trusted geostamping as a tool for meeting traceability needs across multitude of industries. Traceability has different meanings. In the context of precision time and time interval, traceability means an unbroken chain of calibrations that relate to a reference. Each calibration has a documented measurement uncertainty. The desired reference is usually Coordinated Universal Time, or UTC, for time of day synchronicity purposes. In other fields, traceability is about the production and use of markers. Specifically, in provenance scenarios. In digital forms, these markers are for abstract elements such as data, intellectual properties, or events, to inform when, and where, those were recorded, or taken place. In analog forms, these markers serve as evidence, attached to physical assets attesting to their origin, their transit between locations, and chain of custody. These applications of traceability share the universal ground truths of earthbound locations, and UTC timekeeping. The changing landscapes in information technologies have been accelerated by globalization and digital transformation across business segments and their supply chains. Accurate time and traceability to official time sources are becoming increasingly important. For record keeping, IT solutions are now required to generate timestamps representing local time accurately at unprecedented precision. Succinct provenance of certain types of business transaction, intellectual property, data, or physical asset can only be achieved with additional contemporaneous geographic location information. At the same time, certain regulatory bodies impose requirements for better reporting accuracy and transparency in business transactions. The basis of this may stem from legal common law principles and rules of civil procedure. These rules outline the standards for adjudicating disputes and submitting evidence. They spell out time and place amongst other relevant facts for assessing the sufficiency of a legal pleading. That is, the particular material facts of when and where, along with who or what and how, as a requisite to assert a legal claim against a party in a legal proceeding. A geostamp is an atomic data element. It consists of a definitive geographic location and an unambiguously accurate time of day. Its authenticity is established by combining a demonstrably trusted geographic coordinate and a UTC traceable timestamp. This trustworthiness must be in totality with respect to the geostamp issuing system. It begins with the platform hardware and firmware, its GPS interface, its operating system's ability to maintain persistent UTC accuracy, and ends with capable geostamping software tools. This is called a chain of trust. During the second half of 2020, HPE announced its Trusted Supply Chain program, where it is manufacturing selected server models in the United States. Its secure manufacturing facility is staffed by employees that have gone through a stringent background and security screening process. When combined with the scrutiny HPE puts on its supply chain vetting process, these platforms meet the ever-increasing security demands of customers, such as the U.S. government, or those in regulated industries. The ProLiant DL380T Gen 10 server is the first model available from this program. The T designation signifies trustworthiness. Each server is placed into high security mode prior to leaving HPE factory in the U.S. for delivery to the customer. This feature reduces the attack surface for cyber attackers, making it more difficult to inject compromised code or malware into the server firmware. In deployment, the system uses secure boot to ensure that only known good code and OS bootloaders can execute before the Windows Server operating system itself loads. This feature protects the system hardware and software configurations from being tampered in production while the system is not in operations. Windows BitLocker Drive encryption operates with the system integrated cryptographic capabilities to protect data at rest. That is, while the system is powered down, data cannot be tampered by removing its storage devices, altering their contents, and replacing them back in the system. Similarly, should the system be decommissioned improperly, contents of its storage devices cannot be retrieved or otherwise exposed. The Sync and Scale System Interface delivers GPS time and frequency signals, as well as geographic location information, directly to Windows OS via its PCI Express bus. This GPS signal delivery path is not exposed outside of the secure system enclosure. GPS denied condition, due to jamming or inadvertent loss of GPS signals, is mitigated by an integrated oscillator, taking over and maintaining the precision of 1 pulse per second, until GPS signals are restored to the system. Until then, this frequency holdover capability keeps the sync and scale discipline system clock from diverging more than 1 millisecond from UTC for up to 21 days. At all time, the Sync and Scale Windows Certified Kernel Mode driver, since 2012 R2 release, operates with the OS kernel to continuously discipline the system clock several times per second. This keeps the system, its Hyper-V virtual machines, and containerized workloads persistently UTC accurate at microsecond precision. An on-site NIST discipline clock and oscillator instrument, provided by its time measurement and analysis service, was used to characterize this precision of sync and scale-enabled UTC accuracy. Same device can also be used for UTC traceability measurement by continuous monitoring of a system during its operations. We're now showing you a few simple observability steps to determine if your system is persistently UTC accurate, regardless how it keeps time. Samantha will walk us through this demo. Sam?
Thank you. We're looking at a Windows Server 2019 HPE ProLine system. It's operating inside the Microsoft Mega Lab data center, located in Building 88, on Redmond campus in Washington State. The desktop taskbar at bottom includes a display of current time and date at its far right end. This display is updated every 60 seconds, at the top of the minute. A running stopwatch is added above it, as a visual aid, affirming this recording is unedited. The wall clock above it is a 5-year-old Windows Classic desktop app. It is showing the current time of day, according to the operating systems. The control panel, at the upper right corner of the screen, allows an authorized user to set time and date, and timekeeping methods on this system. The system administrator, or an authorized user, can also change the current time of day on this system, using command line interface. That's what I'll do next using the classic command window, on the left-hand side of the screen. I'm using the time command to force time of day on this system to an incorrect one. Let's try 34 minutes, afternoon. Did you catch what the system was doing? How about 15 minutes before midnight? But, before I press the return key, I want you to focus on one of the time displays on the right-hand side of the screen. Perhaps, the wall clock is the easiest one. Ready? Sorry. I forgot to show you earlier. The date and time control panel indicates the system is not relying on network-based time synchronization. Instead, this is a sync and scale-enabled HPE ProLine server. So, what just happened? I entered a valid command. The system accepted and acted on it, as it should. However, immediately, the Windows Server OS kernel was also informed by Sync and Scale that the system had been forced into an incorrect time of day. The kernel took remedial steps to discipline the system clock and brought it back to UTC accuracy. These were reflected by the desktop apps when their displays were updated at the next second boundary. This cooperating interaction between an OS kernel and Sync and Scale system interface happens several times per second to keep system clock persistently UTC accurate. The same interface also delivers GPS geographic location information to the system continuously. This Windows desktop app displays GPS-originated geographic coordinates and corresponding time zone, as well as current system date and time, and its cyberspace time zone. Business needs, or IT rationales, may dictate UTC as the configured system time zone, for all systems making up a solution platform, regardless where they operate geographically. I am now making that change on this system, in its date and time control panel. A sync and scale enabled system provides its true geographic location information, separate from its cyberspace time zone. These two sets of complementary data points allow it to be more versatile and capable for modern IT solutions. The command line app SNS Geostamp is a sample reference tool. It exploits these building blocks on a persistently UTC-accurate system to construct trusted time and place markers. These markers are conforming to the CCT specification. This command creates 3 consecutive geostamps, 5 seconds apart. Accuracy of a geostamp is authentic and can be trusted when the functional integrity of its issuing platform is verifiably definitive and persistent, and data used for its construction are coming through operationally known secure paths. Hal will now dive into more details on how these trusted geostamps are constructed. Back to you, Hal.
Thank you. CCT is short for Common Calendar Timestamp. The CCT system has been developed to resolve ambiguities and inconsistencies in timekeeping specifications and technologies. CCT was originally motivated by standards efforts in the Society of Motion Picture and Television Engineers, and took on the broader goal of creating a uniform and technically accurate representation of local time, in accordance with legal time, and can withstand rigorous scrutiny by a finder of fact. In the U.S., the official national time being maintained by NIST is the legal time for civil and commercial use. CCT constructs timestamps in character and binary formats. The character format takes the familiar human-readable form of a character string. It consists of date and time, and an ensemble of metadata describing local time properties, including leap second, daylight savings and time zone information. The binary format is composed of comparable metadata to facilitate efficient data processing and interchange. The two formats are symmetrically convertible to one another. CCT is an open-source project and being maintained as a GitHub repository. Its implementation is portable across different OS platforms. The Windows tool SNS Geostamp adopts and extends CCT character format to include geographic coordinates in its sync and scale-enabled CCT-conformant trusted geostamps. Each consists of 2 parts, a traceable UTC-accurate timestamp, followed by a trusted GPS-derived geographic coordinate. A casual glance would detect certain familiar information in the geostamp. Let's take a closer look and deconstruct this one, starting from left to right. Date and time is recorded with precision in 100 nanoseconds. It is followed by UTC offset and local time zone name, according to specific IANA time zone database version. Leap second support by the Windows Server OS is called out next. Had daylight savings been in effect, the geostamp would have had that information included at this spot. This one notes the OS timekeeping nuance of different commonly used leap second sequence counting schemes. Geographic coordinate, where the system was located at the time, is described in Cartesian latitude, longitude, and altitude. SNS Geostamp implements a simple checksum of its geostamp, for illustration purposes. More robust methods are recommended for production. Finally, the geostamp string is terminated with the X character. When sync and scale enabled CCT conformant geostamps are examined afterwards, and most importantly, away from their issuing system, this ensemble of local time and date, timekeeping properties, and geographic location information allows the decoding operation to produce consistently deterministic and technically accurate when and where it was recorded. Sarah is going to ground this foundational capability in several scenarios for us.
Thank you, Hal. In Spatial Temporal Geographic Information System, or 4D GIS, the first 3 dimensions represent a geographic coordinate, identifying a physical space. The 4th dimension refers to time. This 4D GIS infographic app by NBC News displays the COVID-19 deaths in the US during 2020 at a very coarse time series granularity. Pop-up and mobile clinics for emergency healthcare delivery during a pandemic or in response to a disaster are likely to be deployed on unoccupied grounds. These are the edge devices of healthcare IT operations. Attempts to correlate these temporary sites with a nearby established location would create confusion afterwards and render collected data less precise. Similarly, attempts to match their assigned identities with recorded data and activities would render collected data less useful for analytics about their environments at different deployments over the course of the response. Geostamping delivered services and associated clinical data, eliminates these potential ambiguities in the records, and improves insights into conditions on the ground. Modern IT solutions that span from edge to cloud would typically be architected to have UTC-accurate and geolocation-aware edge devices. These devices geostamp arriving data and recorded events before forwarding them onto centralized cloud-based storage for aggregation in time series databases. High fidelity of when and where these data points were originated from the edge allows powerful cloud-based artificial intelligence and machine learning engines to produce better actionable insights. Structural organization of geostamps, such as those produced by SNS Geostamp, makes them powerful index keys of time series databases feeding 4D GIS apps, such as the one by NBC News a moment ago. Now, let's step away from the traditional centralized databases and into the modern world of distributed ledgers to see how geostamps play a key role in that field. A ledger is a book or list of data containing information about the outgoings and incomings of specific assets. For example, a bank statement is where the summarized information of money going in and out of an account. It is centrally controlled by the bank and posted as debits and credits on the account statement. A distributed ledger is functionally similar, except it's a decentralized, distributed, and oftentimes public digital version of a general ledger. It's used to record transactions across many computers to ensure it cannot be altered retroactively without the alteration of all subsequent entries. These computers belong to a consortium of different organizations. They run programs that are obeying an agreed protocol among members of the consortium. They don't all have to be the same program. They just need to all conform to the same communication protocol. That protocol coordinates the exchange of transactions and the generation of corresponding information blocks linked together in a chain representing ledger entries. Collectively, distributed ledger technologies are called blockchain. Three main attributes of a block or a distributed ledger entry are what, when, and where. The what is a description of the transaction. The when is not just a calendar date and time of day at the recording moment. Distributed ledger entries must be in chronological order and unambiguous. A recorded transaction must be verifiably demonstrated to have taken place prior to another, or concurrently. That is, money is to be received before it is spent. Spent money cannot be spent again. Similarly, goods from producers need to arrive at a depot before they are forwarded to retailers, and so on. The where is a definitive geographic location if a transaction is subjected to regulatory requirements and enforcement of a jurisdiction. Remember, IT cloud is not a geographic location in the sky. A properly constructed distributed ledger entry using sync-and-scale-enabled CCT-conformant geostamp can be examined afterwards by any member organization of the consortium for determination of when and where the transaction was recorded or taken place. The end-to-end process, from sourced raw material to final product sold to a customer, is called a supply chain. Effective supply chain management is a challenge in every industry. In healthcare, a compromised supply chain can directly impact safety of frontline workers and risk patient health outcomes. Among the emerging use cases of blockchain is for combating counterfeit personal protective equipment including clothing, helmets, goggles, masks, or other garments or equipment designed to protect the wearer's body from injury or infection. Each additional block in the chain attests to the true manufacturer at origin and when and where these products were moved among distributors in the supply chain. So, in these scenarios, geostamps enhance the effectiveness of existing solutions and enable new ones. I'll let Hal pick up the presentation from here.
Thank you, Sarah. In conclusion, a trusted geostamp is an atomic data element, consisting of a geographic location and a timestamp. Its authenticity is established by combining a demonstrably trusted geographic coordinate and a UTC traceable accurate timestamp. It is human-readable and technically accurate for interpretive and forensic purposes. It can be examined afterwards and away from its issuing system, for determination of where and when it was recorded. Mature state-of-the-art software and hardware capabilities exist that can realize these properties required of trusted geostamps. The common calendar timestamp system allows apps to be developed and operated on sync and scale-enabled UTC-accurate and geolocation-aware Windows Server platforms. Their produced geostamps are suitable for general and legal purposes, where time recording is used for tracking and auditing. Thank you for watching.